Okay, let's go through the learning check from class this week where we were looking at carbocation stability. We'll go through each row at a time. So first we are looking at each molecule and determining if the carbocation is primary, secondary, or tertiary. So let's first remember what that means. We could have a carbocation. Well, all carbocations are bonded to three things, or it has three bonds. If we have two hydrogens and one of the bonds goes to a carbon, or in this case an oxygen or a nitrogen, just something that is not a hydrogen, we call this primary. If the carbocation is bonded to two R groups, so that would be two non-hydrogen atoms, that would be secondary. And then if a carbocation is bonded to three R groups, three non-hydrogen atoms, that will be tertiary. All right, so our first molecule, the carbocation, is this carbon. And so this carbon is bonded to two hydrogens. That's written as a CH2, but you can imagine it has a bond to one and a bond to another, and then it has a bond to this carbon. So this carbocation is bonded to one carbon, that makes it primary. You could write that, or you could write, just so I have more space, you could write the word primary. You should know that you can use this to represent primary just in case you see it elsewhere. Okay, so that's our first molecule. The next molecule, our carbocation, is, let's just highlight these. So is that center carbon right there. That carbocation is bonded to three carbons, two carbons in the ring and then the carbon in the CH3 group. So this is a tertiary carbocation. Next molecule, carbocation, is right there. It is bonded to one hydrogen. Remember, there are implicit hydrogens. And then one carbon and this oxygen. So the oxygen counts like an R group. It's a non-hydrogen atom. So it's bonded to one hydrogen, a carbon, and an oxygen. That makes it secondary. Last molecule, carbocation, right there. It is again bonded to one hydrogen. So it's bonded to a hydrogen and two carbons, secondary carbocation. All right, next question is if the carbocation is stabilized by resonance or not. I'm going to erase what I have drawn on each of these molecules. Oops. Just so we can see each one a little more clearly. All right, so we had seen an example of a carbocation stabilized by resonance. Let's just do this for example. I think this is what was in our notes. And it doesn't have to be an oxygen, even though that's what we're looking at in the structures on this learning check. It could be a nitrogen. It could be any other atom with lone pair electrons. When the atom with lone pairs is bonded to the open shell carbon, this is one of our types of resonance we've seen in our earlier unit. A lone pair from that oxygen can be shared as a double bond between the oxygen that owned the lone pairs and then the carbon that's open shell. Because it's open shell, only has three bonds, it can accept more. Okay, let's look at each structure. And just to emphasize where lone pairs are, I'm going to draw them on the oxygen. So the question is, could these electrons resonate to the open shell carbon? Well, between the oxygen and the open shell carbon, we have another carbon that has four bonds. That's an sp3 carbon. It can't accept any more electrons and it can't give away any electrons. We actually have another one in between the oxygen with lone pairs and the carbocation. So let's do some highlighting. These two carbons are sp3 carbons. They cannot resonate any electrons. They can't accept any electrons. So there is no way for a lone pair to get up to this carbocation. So this is not stabilized by resonance. And this is what we will look for in each molecule. Second carbocation molecule, again, just drawing these lone pairs, but we have the same problem between the carbocation and the oxygen with lone pairs. Doesn't matter if you look on the right side of the ring or the left side of the ring. There are two carbons that prevent electrons from resonating to the carbocation. So this is also not stabilized by resonance. In the third structure, the oxygen is bonded to that carbocation, and so it is possible for these electrons from the oxygen atom to resonate and form a double bond. I'll just draw that right above so you can see the result of this resonance. Look like this, where we now have a double bond between the carbocation and the oxygen. The oxygen still has one lone pair, and the oxygen becomes positive. This is possible because the sp2 carbocation, is adjacent to the oxygen with lone pairs, or the atom with lone pairs. All right, lastly, we have, again, oxygen with lone pairs. Between the carbocation and the atom with lone pairs, we again have an sp3 carbon that's preventing the resonance of electrons. So this is not stabilized by resonance. All right, now we're looking for the most stable carbocation. We know that primary and secondary generally are least stable carbocations. But we also know that resonance stabilizes a carbocation. We know that tertiary carbocations are stable. So we really need to compare the stability of these two carbocations, the tertiary one and the resonance one. Well, in the carbocation that has resonance, there is another significant resonance structure where the carbocation isn't a carbocation anymore. It's a closed shell. All atoms are closed shell. That is more stable than a tertiary carbocation. So we can generally look for primary, secondary, and tertiary, where tertiary will be the most stable. But if resonance is possible, that will make that carbocation the most stable. So this is the most stable carbocation due to resonance. And if you look at our notes, when we were talking about carbocation stability, they pretty much look like, all of this up here, where we said primary, secondary, tertiary, and then stabilized by resonance. Secondary is least stable, primary least stable, then secondary, then tertiary, then resonance stabilized. All right, the last row, placing an X in the box for the least stable carbocation, that's our primary carbocation. So that's this box here.